We have learned that the integral is the antiderivative and the area underneath the curve. So this is climb time. And in this video, we're going to look at a specific example at the antiderivative being equal to the area underneath the curve. All right, so the specific example I'm going to look at is the integral of 2 minus 2x dx from -1 to 4. So 2 minus 2x is our function. And so we know that the integral is two things. One, it's the underneath the curve. And two, we know it's the antiderivative evaluated at 4 and -1. So we're going to show that these two come out to be the same thing. So I already started with 2 points on my graph. I have a point right here, which is going to be the y-intercept 2. And because we have a slope of -2, that means we go down 2 and over 1. So those 2 points are 2 points in our graph. I know if I go down 2 again and over 1, I'm going to get another point. This is the line. So here's 3 points on my graph. I'll do my best to graph it as straight as possible. Okay, and so that's what our line looks like, and we want to find the antiderivative. And so one of the nice things about the antiderivatives is that it'll give you an exact answer, whereas when you find area underneath the curve, a lot of times, depending how you're finding it, if you're finding a Riemann sum, you're getting an approximation in many cases. But if you're using a geometric formula, again, you'll get an exact answer. So it depends how you're finding area underneath the curve. But one of the advantages of finding an antiderivative is it will always give you an exact answer. So let's look at our 2 points, -1 and 4, because I think it's helpful to see what we're looking at here. So -1 is here. So that means, and this may not be completely to scale, and that's okay. That means we're looking at this area here. Okay, that's one of the spots. And then also to 4. So if I take this out to 4, so 3, 4, and I go down from there. So I'm looking at this area here as well. Okay. All right, so we're looking at the area underneath the curve. 2 minus 2x is our function, and it's from -1 to 4. So that means -1 is our lower bound, 4 is our upper bound. We can see we have some positive area, and you can see we have some negative area. All right, so I'm going to start by looking at what happens when I find the antiderivative. So the antiderivative of 2 minus 2x, basically I can use the sum rule for derivatives and integrals, which allows me to take the integral of 2 and take the integral of 2x as separate integrals. So I have 2 and 2x, and I can basically separate that out and take the integral of each one separately. And it's still -1 to 4. I'm not going to write it in, but it's still -1 to 4. So the integral of 2 is going to be 2x. And the reason why is because if I took the derivative of 2x, I would get 2. So whenever you take the derivative of a coefficient times the variable with respect to that variable, it always becomes a coefficient. And the reason why is because a derivative is the slope of the tangent line, and the slope of this tangent line would be 2. You can also use the power rule as well. Power rule works as well. And so that means whenever you have a constant, you can just slap the variable on there. If you're doing the antiderivatives. The antiderivative is just going backwards from the derivative. All right, and so on this one over here, I have minus, and what I'm going to do is I'm going to add 1 to the power. So the power is 1, so I'm going to add 1 to the power. So it was 1 before, now it's 2, and I'm going to divide by the new power. Okay, so it's 2x squared over 2. And because this is a definite integral, I didn't write them in here. Maybe I should have, but because it's a definite integral, that means we have to plug in these values, -1 and 4. So I'm not going to plug them in yet. I'm going to first simplify here. But that's how you go about finding the antiderivative. You find the antiderivative of each term. And you could use the power rule here as well in that case. But anyhow, 2 becomes 2x and add 1 to power. So you get 2 divided by 2. And these cancel out. And so what we get is 2x minus x squared evaluated at 4 and -1. So 2x minus x squared evaluated at -1 and 4. All right, so now the way we do this is we have to plug in the 4 and we have to plug in the -1. And so if I do that, I'm going to get 2 with a 4 plugged in minus x squared with a 4 plugged in. And what this represents the antiderivative evaluated at 4, the upper bound. So the antiderivative evaluated at 4. And then minus the antiderivative evaluated at -1. So I'm going to plug in -1 everywhere I see an x. So 2 times -1 minus -1 squared. Okay, so again, this represents here, maybe I will circle that. This represents here the antiderivative. If this is little f, this is capital F, evaluated at what we'd say b, which is our upper bound, 4. And this represents the antiderivative, which is capital F, evaluated at -1. So f of b minus f of 1. So one of the definitions of the integral, or one of the things the integral becomes, is the antiderivative, but it's the difference. And if it's a definite integral with two bounds, it is the difference between the antiderivative evaluated at the upper bound and the antiderivative evaluated at the lower bound. And so this is one way to find, to evaluate a definite integral. It's also a way to find the area underneath the curve because it should come out to be the area underneath the curve. All right, let's simplify this. So I end up getting 8 minus 16. I'll just write that in, 8 minus 16. And over here, I end up getting minus, that's -2, and then minus 1. So -2 minus 1. All right, so I end up getting 8 minus 16, which is -8, and then minus -3, which is +3. So I end up getting -8 plus 3, which is -5. Okay, and you can check my math on that. It comes out to be -5. And so what that means is it must be that the area also comes out to be -5 because it involves two things. It's the antiderivative evaluated for a definite integral at b and a, and it's the difference between the two. And it's also the area underneath the curve. So let's take a look at the area underneath the curve now. What does that come out to be? All right, well, if I look at this one right here, I'll say that the area will come out to be, I'll say just A1, and A1 will represent this right here. That's A1. I'm just going to find the area there using the triangle, the area of a triangle, and then A2 will be right here. And because A2 is below the x-axis, that one's going to be negative. So the total area is going to be A1 minus A2. So let's see how that works itself out. All right, so we have a triangle there, so it's going to be 1/2, and I'll just say B1 times H1. So it has its own base, it has its own height, minus 1/2, and I'll call this B2 times H2. All right, so since this hits the x-axis at 1, that means the base for this first one is 2 because it goes from -1 to 1, so the base is 2. So this becomes 1/2 times 2. And then I have to figure out what the height is here. And so to figure out the height, I could probably just work my way over using slopes. But another way to do it is to actually plug -1 into the function. So if I plug -1 into the function, I get -2 times -1, which is +2. So 2 plus 2 is 4. So that should come out to be 4. So I would expect this to come out at 4. So the height of this first triangle should be 4. So I'll plug that in there. I have minus 1/2. And then this base is the difference between 1 and 4. So this base is 3. And then the height, I can plug that into my equation here. So I'm looking at 4. So when x is equal to 4, what is the y value? And it will come out negative, but I've already accounted for the negative right there, so I don't have to worry about the negative sign. So when I plug in 1, 2, 3, 4, 4, I get -2 times 4 is -8. So I get 2 minus 8, which is -6, but I'll just call it +6 here because I already accounted for a negative right there. All right, so let's see what this comes out to be. So I get 1/2 times 8, and I get 1/2 times 18. And so 1/2 times 8 is 4. 1/2 times 18 is, no, oops, I forgot my sign. My sign should be minus. There we go. That should be minus because there's a minus there. Should be minus here. So 1/2 times 18 is 9. So minus 9. So it equals to be -5. So not surprisingly, I get the same answer, whether I find the area underneath the curve using geometric formulas, or I find an antiderivative and I plug in my lower bound and my upper bound. So the difference in values of my antiderivative will give me the exact same result as the area underneath the curve. And I did this with geometric formulas. So I just want to reiterate something I said before, and that is that when you use the antiderivative, you will always come out with an exact answer, assuming you don't simplify if you have something that's irrational or pi or whatnot. So you can come out with an exact answer through the antiderivative. But if you find the area underneath the curve, you may not get an exact answer depending how you do it. If you use geometric formulas, yes, you'll come up with the exact answer. But in many cases, geometric formulas, it's not obvious what geometric formula to use, or if there even is a geometric formula. So a lot of times we'll use Riemann sums. And if you use enough Riemann sums, you can get close enough to the actual value. But in that case, it is going to be an approximation. So that's one thing that's different between the two, is even though they are equal to each other, if you have an infinite number of Riemann sums, a lot of times it is not possible to actually have an infinite number of Riemann sums. And so if we're finding the area underneath the curve, then we will usually get an approximation. However, what we do know is that this is always equal to this. If you could get an exact area underneath the curve, then we know it will be equal to, exactly equal to the antiderivative with the bounds plugged in. So this is an example of how the integral, a definite integral, is both an antiderivative and is also area underneath the curve.